Hey everyone, welcome back to Chem Story. Today, we're diving into a really important topic, the stereochemistry of the E2 reaction. Now, you probably already know that E2 follows a one-step, concerted mechanism. But to truly understand how and when it happens, we need to take a closer look at the spatial arrangement of atoms. So, why does this even matter? Because in E2, geometry isn't just important, it's absolutely essential. Let's break it down. So, what does it take for an E2 reaction to run smoothly? Well, first off, bond breaking and bond forming happen at the same time. That means everything needs to be in sync, especially the way electrons move during the reaction. For that to happen, proper orbital alignment is key. The orbitals involved in breaking the CH bond and the CX bond need to line up perfectly with the pi bond that's forming between the two carbon atoms. In other words, all of them have to lie in the same plane. This is what we call stereoelectronic alignment, and without it, the reaction simply won't happen, no matter how strong your base is or how great your leaving group might be. So yeah, getting this alignment right is absolutely crucial for a successful E2 reaction. Now let's talk about one of the key geometries in the E2 reaction, the anti-periplanar arrangement. To see why this matters, we first need to understand what periplanar actually means. It simply means that two atoms or groups lie in the same plane, relative to a single bond. And this kind of alignment is super important because it allows for proper orbital overlap, and that's what makes electron flow smooth and efficient. There are two main types of periplanar arrangements. In the Syn-periplanar conformation, the two groups are on the same side, with a dihedral angle close to 0 degrees. But in the anti-periplanar conformation, they're on opposite sides, with a dihedral angle near 180 degrees. And for the E2 mechanism to work, this anti-periplanar geometry is absolutely essential. That means the beta hydrogen and the leaving group have to be positioned on opposite sides of the same plane, almost like they're facing away from each other. Now, what about the Syn-periplanar geometry? In this case, the beta hydrogen and the leaving group are on the same side of the plane, kind of like an eclipsed conformation. But this setup is a lot less favorable, mostly because of torsional strain. When the bonds are lined up like that, the electron clouds in the CH and CX bonds get too close. They start to repel each other, and that pushes up the overall energy of the system. On top of that, it throws off the orbital alignment, so electron flow becomes much less efficient. Now, technically, E2 can still happen with this geometry, but it's pretty rare. You usually see it in rigid cyclic systems, where the molecule is basically locked into that Syn-periplanar arrangement. Let's take a closer look at how E2 elimination depends on anti-periplanar geometry, using this example. Here, a brominated alkane reacts with a strong base, sodium hydroxide. Since E2 is a concerted reaction, bond breaking and bond forming happen at the same time. In this molecule, there's only one beta hydrogen available for elimination. And for the reaction to work efficiently, that hydrogen needs to be anti-periplanar to the leaving group, bromine. In other words, the beta hydrogen and Br have to lie in the same plane, but point in opposite directions. This alignment lowers the activation energy and helps the reaction proceed more smoothly. If the molecule isn't already in that conformation, it has to rotate into position first. Once everything's lined up, the base grabs the beta hydrogen. At the same time, electrons from the CH bond move in to form the double bond, and Br leaves. The result is an alkene with an E configuration, where the higher priority groups on each carbon of the double bond end up on opposite sides. And that E configuration? It's not a coincidence. It comes directly from the anti-periplanar geometry during elimination. Let's look at another example that also follows the E2 anti-elimination mechanism, but gives a different stereochemical outcome. Just like before, the beta hydrogen and Br need to be anti-periplanar, but this time, the twist comes from the orientation of the methyl group. To get the right alignment, the molecule has to rotate. And in that conformation, the two phenyl groups end up gauche to each other. That creates some steric strain in the transition state, which makes the reaction a bit slower. Still, elimination happens. And this time, the product is a Z-alkene, where the higher priority groups are on the same side of the double bond. So once again, we see that E2 is stereospecific. The exact geometry of the starting molecule directly controls both the stereochemistry and the reaction rate. Let's take a quick look at Syn elimination. Even though it's rare, E2 reactions can go through a Syn-periplanar transition state, but usually only when anti-periplanar geometry just isn't possible. A good example is a bicyclic system. In this case, the beta hydrogen and the leaving group, like a tosylate, can't adopt an anti-periplanar alignment because the ring is too rigid. So instead, the reaction goes through a Syn-periplanar pathway, and you get a 100% Syn E2 product. The key takeaway? When anti-elimination isn't an option, the reaction can still happen, as long as the geometry allows it. Another classic example of Syn elimination is the coelimination. In this reaction, an amine oxide breaks down upon heating to form an alkene, and the key here is geometry. The structure of the molecule forces the beta hydrogen and a leaving group into a Syn-periplanar arrangement. So this becomes a textbook case where elimination happens, even without anti-periplanar alignment. Now, anti-elimination is still the preferred pathway. But Syn elimination can definitely happen, especially in rigid or constrained systems where anti just isn't possible. Let's talk about how E2 eliminations work in cyclohexane rings, where the molecule's conformation plays a major role in whether the reaction can actually happen. For E2 to occur, the beta hydrogen and the leaving group need to be anti-periplanar. In cyclohexane, that means they both have to be in axial positions, on opposite sides of the ring. This is known as the transdiaxial rule. If either one is in the equatorial position, the alignment just isn't right, and the reaction won't happen. That's why a ring flip is sometimes needed to bring both the beta hydrogen and the leaving group into their axial positions before elimination can take place. Let's look at an example. Here, the halogen, let's call it X, starts off in the equatorial position, which is more stable. But in this conformation, E2 can't happen because X isn't axial. Now, if the ring flips, the leaving group moves into the axial position. And once that happens, it lines up perfectly with an axial beta hydrogen on the opposite side. That gives us the transdiaxial conformation we need. And now, E2 can proceed smoothly. This shows something really important. Even if elimination looks possible on paper, conformational constraints can totally block the reaction, unless a ring flip happens first. Here's an example where E2 elimination just doesn't happen. At first, the leaving group, let's call it X, is in the equatorial position. And in that conformation, the reaction can't move forward. Now, after a ring flip, X moves into the axial position, which is exactly what we want. But here's the problem. All the beta hydrogens are still stuck in equatorial positions. And without an axial beta hydrogen, elimination is off the table. So what does this tell us? In some substituted cyclohexanes, E2 isn't just about the base or the leaving group. It's about whether the molecule can achieve that transdiaxial geometry. And if it can't, the reaction simply won't happen. Now let's look at a different case. After the ring flip, the leaving group, X, ends up in the axial position. And this time, there's only one axial beta hydrogen available. But that's enough. Elimination can still happen. It just has to occur at that specific position. So you end up with one major product. This is something really important to keep in mind when predicting E2 regioselectivity in cyclic systems. If there's only one axial beta hydrogen, the reaction will give you a single alkene product. In this case, after the ring flip, the leaving group becomes axial, and now there are two axial beta hydrogens available. That means elimination can happen at either position, and that could give a mix of alkene products, but usually one of them is favored. According to Zaitsev's rule, the more substituted alkene tends to be the major product. So what's the big picture here? E2 reactions aren't just about having a strong base or a good leaving group. The real key is geometry, especially that anti-periplanar alignment that makes elimination possible. Once you understand this stereoelectronic requirement, you can start predicting whether E2 will happen, what conformation the molecule needs, and what kind of alkene product you're likely to get. In the next lesson, we're shifting gears, and we'll take a closer look at E1 and E1CB mechanisms, how they work, when they happen, and how they're different from E2. Thanks for watching, and I'll see you next time.